Good morning. So we finished one section of this course now, the part on geometric optics, and we are starting on the next part, which is on Gaussian beams. So it's a big change because up till now we've been considering that light travels in straight lines and we're considering rays, and the moment we go to Gaussian beams or any kind of solution to the wave equation, then you're no longer thinking of light as simply rays, but you're thinking of it in terms of waves. Now, there are many reasons why we study light in this way, and those reasons will become clear as we go along the course. One point to note is that in many applications today, the source of light that we use is a laser. Okay, that you would have heard laser diode. If many of our small systems will have laser diode, many larger systems will have different kinds of gas lasers or variety of lasers. And the typical output of a laser, so this is, if I had to pick and say what is the output of a laser, the light coming out of the laser can be in a variety of modes, but the typical output of a laser is a Gaussian beam. Okay. So that is one very crucial reason why we look at Gaussian beams. Okay. Now, I can approach this in another way. I could ask the question, can light be spatially confined and transported in space? And again, to answer this, I'm going to look at the different kinds of beams that exist. Now, what do I mean by spatially confined? That means as this beam propagates, does it spread out and occupy all of space, or does it travel? So it's propagating. So transported means it's propagating. As it propagates, does it propagate with a more specific direction, or does it spread in space? So again, we use lasers. The most typical output is a Gaussian beam, and when I'm looking at beams, what is the usefulness of the beam? We are always thinking, how can I manipulate light in some way? And it most often is useful if you can confine that beam as it travels. Now, you would have heard of different kinds of beams, different kinds of waves. So, you might have in any electromagnetics course, you would have definitely looked at what is called a plane wave, right? I see no recognition on anyone's face. Okay, so if I write the equation of that represents a plane wave, I will have the amplitude of the wave, and then I have a term that takes into account the phase of the wave, right? So that shows it's complex, right? And it's kz minus omega t. What do these different terms mean? I'm talking about the amplitude, this entire term in the bracket is the phase, but this relates to the frequency, or I can relate it to the wavelength of that wave, and this to the propagation direction, that z is the propagation direction. You could think of a spherical wave. And in a sense, these two kinds of waves are sort of completely opposite in nature. Right? Because what is the property of a plane wave? As it propagates, you can see from this equation, it's propagating in one direction. Okay, so it's propagating in the z direction, but it's not a practical wave. I can never realize this wave in a lab. When I say this wave, I mean what is expressed by this equation. I can never realize this exactly, because the amplitude, if you see, there's no specification on what is the relationship between the amplitude and the transverse coordinates x and y. So if you look at this expression, it's actually saying this amplitude A, it spreads out infinitely. So if you might have seen pictures of a plane wave, and you may have seen it drawn something like this, right? So these are the different planes of the plane wave. This is the direction z. Now when they draw it like this, they're drawing this finite square shape or finite rectangular shape. But that's just because they want to show you something in the book that you're looking at. In reality, there's nothing in that expression that says the amplitude spreads over this finite distance in the x and in the y direction. The way I've drawn it here, there's a finite spread. In the equation, it is an infinite spread. So actually, this mathematical equation, though you might have seen it many times before, may not have realized that it implies I'm talking about a wave with infinite energy. Okay? What are these squares that we are drawing? These are what we call the wave fronts. Okay. So for any wave, when I discuss a wave, when I talk about a wave propagating, I will use the wave fronts as one means of describing the propagation. Okay? And what is a wave front? A wave front is nothing but a surface of constant phase. So of course the wave exists throughout the medium, but I'm drawing at one position where the wave has, and here it's a plane wave, over this entire surface is constant phase. And then we draw the next wave front where it has traveled an optical path length that gives it back the same phase it had over here. Okay, so equivalent to a distance of lambda. Okay, the phase that is acquired after traveling a distance lambda. So while this is interesting to look at, while I might be able to arrive at some simplified version of this in a lab, this expression by itself represents a wave with infinite energy and is not something that is actually produced in the lab. However, I'm interested in it because it gives me the type of wave which has one direction that it travels in, and it travels consistently in that one direction. The spherical wave, on the other hand, is completely opposite. It starts from a point, and the wave fronts emerge as spheres around that point. So when I draw it on a two-dimensional surface, it's going to look like circles, but the wavefront is a sphere about the point. And as you move away from the source, which is the origin of this wave, the spheres go on expanding in size. Okay, so there's no one direction this wave is traveling in. It's traveling, in fact, in all directions. So two very opposite waves of very different behavior. And we study them because some simplified versions of these are achievable in the lab and are used in actual experiments. But they're not exactly a description of what we're seeing, and they're definitely not a description of what is emerging from a laser. So we go back to the Gaussian beam. And apart from the fact that this is a typical output of a laser, it also has some properties that make it relatively nice to study. Okay, so it turns out that the Fourier transform of a Gaussian beam is going to be a Gaussian beam again. And this is important when you're looking at propagation, because I can use the Fourier transform operation to understand what happens to a wave as it propagates. So this is a nice result. This is a nice fact. It turns out that of all the different beams, the Gaussian beam suffers the least diffraction. Okay. So in addition to it being the beam that we're typically going to get as an output, it also has some nice properties that make it useful. Now, we are thinking of the Gaussian beam as a solution. We know the output of a laser is a very directional beam. Right? The beam emerging from a laser doesn't immediately start diverging. Right? It's a very directional beam. So, in that sense, it is similar to the plane wave. Where it differs greatly from the plane wave is the fact that the plane wave stretches out to infinity in the transverse direction, right? And we know that the beam emerging from the laser, it has a finite width. That means if I were to look at the amplitude of the wave in terms of x and y, considering that it was traveling along the z direction, I know that at some large value of some value of x, so for some x naught and for some y naught, this a would tend to 0. So for larger than x naught and larger than y naught, a would tend to 0. That means the beam has a finite diameter. It doesn't spread out to infinity. Okay? So we are not going to do a derivation, a formal derivation of the Gaussian beam here. If you are interested, one of the earliest papers on Gaussian beams was by Kojelnik. So the authors were Kojelnik and Lee. It is, I think, a 1966 paper that appeared in the journal Applied Optics. Okay, they study this beam in more detail and give you the mathematical derivation. So if you're interested for more information, you can get it from there. And see if we can arrive at something that seems to satisfy the Gaussian beam. Okay, so I know that I want to consider a beam that has a finite spread in the x and y direction. Okay, so I'm going to guess, I'm going to make a guess that it has some relationship like this, where this omega, so if I consider the width, the transverse spread of the Gaussian beam, then we consider this width as 2 omega. Okay. The plane wave in terms of phase had a jkz term in it, right? This was a phase acquired as the wave traveled along the z axis in the z direction, right? So this was the phase. What is that k? The k is the wave number. It's 2 pi by lambda, right? And of course, it would be 2 pi n by lambda if this was in some medium. Right? So that lambda, you can consider, I could consider it as it's 2 pi by lambda naught, where lambda naught is the wavelength in air. And if it was some other medium, it would be this. So I could write this as 2 pi lambda, where that's the wavelength in that medium. Okay. So this into z is optical path length. Sorry, yeah, that n into z is optical path length, and this into 2 pi is the phase that is acquired as the wave travels. Okay. So my plane wave expression had this term. This is how the phase was changed in the plane wave expression. We are looking at a beam that is not exactly a plane wave, it's not exactly a spherical wave. How would this look if I was looking at a spherical wave? If I had, so this is a phase of a plane wave. If I was looking at a spherical wave, I would have JKR, right, where R is x squared plus y squared plus z squared. Now, I know my Gaussian beam is not exactly a plane wave, is definitely not a spherical wave. So, I am going to do a modification of this term. How is it different? We say that we are worried about, or we want to take into account x and y in terms of the amplitude. So, we are considering a beam now that has a finite lateral spread, but that lateral spread is small, doesn't extend to infinity at all. So, it's a good assumption to say that the variables x and y that we are going to consider for our wave are going to be much less than the distance over which the wave is traveling. Okay, so the beam is spread over a very finite lateral distance, and it is very small. Those parameters are small compared to the distance traveled. Now, if I do that, I can rewrite this as so my phase, then I could consider it to be e pi j k r, but in this case, because of this assumption, the r reduces to e pi j k z, that's the first term, into e pi j k x squared plus y squared by 2 z squared. We know the way the Gaussian beam propagates, and we're trying to arrive at, we're making some intelligent guesses and trying to arrive at what could the behavior of the wave be, what could the expression be based on its behavior, based on what we know about the plane wave and the spherical wave. Okay. So, if I write out then the wave equation for a Gaussian beam based on my assumptions, since we've not done a formal solution of the wave equation, I can't assume that what I write down based on these assumptions is exactly the wave equation for a Gaussian beam. But I know that it should have terms similar to these terms. And so if I write down what I know, it should have a term, so maybe there is some a naught e power minus x squared plus y squared by omega squared, right, and e power j k z minus, I'm taking the time into account, and e power j k x squared plus y squared by 2 z squared. You can already see it's way more complicated than either the equation for a spherical wave or a plane wave, right? And that's one of the reasons when you first solve the wave equation in electromagnetics and you study waves, you're generally just given these equations of the plane wave and the spherical wave, because that helps you understand how you can get different solutions to the wave equation. Yes? The extent of the wave. I'm talking about a wave that's traveling. So his question is, where did this arrive? Why did this arise? I'm talking about a wave that's if I was looking at a plane wave I could consider as traveling like this. But I've drawn it here with this finite extent. But actually, according to the plane wave equation, this, if I call this W, I'll say W tends to infinity. the plane is infinitely large. The equation for a plane wave is a e power or exponential kz minus omega t, right? I have no xy component there. There's nothing limiting the amplitude a in terms of x and y. So the mathematical expression means this actually spreads across infinity, right? But that's not a true solution, because if the wave actually spread across infinity, it has infinite energy, and I mean, of course, we can never generate such a wave. So we are making the assumption that I'm now saying the way I draw, I'm drawing this. I'm saying I'm considering a wave of finite width. In other words, the spread of the wave in this direction and in the orthogonal direction, so in the transverse plane, that those dimensions are much smaller than the distance over which the wave is traveling. And that's why I arrive at this. So it's too detailed to work out the formal derivation of the Gaussian beam. It's not required for this class, but I want you to get the idea that, and from you all ought to have done some course in wave propagation or electromagnetics before this. So you would have arrived at an equation, a wave equation, and you should have also studied the fact that there are many different solutions to the wave equation, right? The point that you need to understand here that is of importance here is many of those solutions you would have studied earlier were mathematically ideal solutions. Then they're not really what we generate in a lab. They're not really what emerges from a source like a laser. Now, I'm trying to use the knowledge that you had there to give you a sense of how we can consider the Gaussian beam, which is a real solution to the wave equation, a practical solution to the wave equation. So based on these assumptions, I modified or used our ideas of the plane wave and the spherical wave to arrive at this expression over here. I would expect that the Gaussian beam expression is of this form, okay? So now what I want to do is I'm going to give you the derived solution. I didn't want to throw that equation at you because it has a lot of terms in it. And if I just give you the Gaussian beam equation, you'd say, where did all of this come from? So this few minutes should have given you some background as to what is the origin of these different terms. Okay, we can't explain every term of the actual Gaussian beam with this hand waving argument, right? But at least some of the terms should make more sense to you now. So what I'm going to do now is to write out the expression, and this is an expression arrived at from a formal derivation or a formal solution to the wave equation, taking Gaussian beam conditions into account. Okay, so the actual Gaussian beam equation, and it's a slightly complicated equation, so I want to get it right, is, let's say I say it's E, which is a function of r and z, okay, and actually let me not say r because I used r earlier as this, and I want this variable, I'll call it rho. Rho is now just x squared plus y squared. It's just a function of the transverse coordinates, okay. So there is some amplitude a naught, and I'll explain what these different terms are. Minus rho squared by omega squared z exponential minus jkz minus jk rho squared by capital R squared of z, this is 2 plus j, and this is zeta. Okay, I'm not drawing that very well, zeta of z. Okay, this is the actual expression for a Gaussian beam. Now, some parts of it, with any wave equation, you must recognize the main parts of the wave equation, the expression for the wave, right? What are the main parts? You have a set of terms that relate to the amplitude of the wave. right? And you have an exponential, and everything in this bracket relates to the phase of the wave. You can see it's way more complicated than either the expression for a spherical wave or a plane wave, right? In fact, I didn't write out the expression for a spherical wave, but that would be jkr a by r, because as the wave propagates in the radial direction, at any point its amplitude is dropping, right? So the power is constant. So while you may not understand each of these individual terms in this Gaussian beam expression, you can still see, as any expression for a wave should have, for any wave, there must be an amplitude term and there must be a phase term, and we can see that here. You should also be able now to see some similarity between the expression we arrived at, taking into account some assumptions that modified the plane and spherical wave, right? And what were those assumptions based on? We said, given that what we know about the Gaussian beam, it is a beam of finite width. It does not spread in the xy direction. We arrived at some expressions like this, right? And you can see that mirrored over here. Remember, rho squared is x squared plus y squared. So it's a function of the transverse coordinates. This this term is relating to this part. We have not written out the time dependence. I have written only the spatial dependence here. Okay. We can always study only the spatial dependence, because your e to the power minus j omega t is going to repeat everywhere. So you can always just study the spatial dependence, and finally, if you actually need the full wave at any point of time, at any instant of time, you will take into account that e power minus j omega t term. So we've written only the spatial dependence of the Gaussian beam here. So that's why you don't see the term minus j omega t. I can write that. It doesn't give me any information about the spatial extent of the wave. So this has been taken into account. This has been taken into account here, right? So I have expressions which take into account some of the phase varying terms in my Gaussian beam. I do have some extra terms. I have this term and this term. Okay, and those, of course, you would understand if we did the formal derivation. What is important for you now is to have a better sense of these terms in this Gaussian beam, to get an idea that now we are talking about or discussing a beam that it travels more or less in one direction, the z direction, but it does have a finite spread indicated by this, and that spread is taken into account in the amplitude, right? This is coming in the amplitude, which means that the amplitude doesn't spread out to infinity, right? And as we go along, the other terms will become clearer. Why are there other terms? Because if I write down expression for any wave, what is each term in that expression doing? It gives us the information of how the wave changes as it propagates. Right? And this idea that propagation itself does something to the wave should not be new to you, because even in ray optics, we considered propagation through free space as an operator, as an optical operation. So if you did nothing and you let your ray travel through free space or a homogeneous medium, it changed some parameter of your ray. And that's exactly the same with any wave, any beam. As it travels, the very act of traveling changes the beam. And that's why we classify beams into plane waves, spherical waves, Gaussian beams. There are a multitude of beams. You might have in your life up till now heard of plane waves and spherical waves. But you have Gaussian beams, you have Hermite Gaussian beams, you have Laguerre Gaussian beams, you have Inchy beams, you have Methau beams, and that's just a fraction of the beams. Now, what does each of these names mean? It means you're talking about a class of beams or a set of beams which have a specific behavior as they travel. The way they change as they travel has some specific property. Okay? So, the Gaussian beam needs this complicated expression in order for us to calculate or to understand that if I know all the parameters of the beam at one plane, what does the beam look like at some other plane, right? So, I may have measured the beam parameters at one plane and I allow this beam now to travel. I may need to know what are the parameters at another plane. Even in your optical design system, if you don't know the parameters, if you don't know how the phase of the beam has changed, you cannot design a lens that will give you focus, because the lens assumes that it will focus a beam given it has a certain input phase on it. If you're miscalculating the input phase and you're saying, I'm going to use this phase to change the beam in this way, if your input phase is wrong, the optical element is not carrying out the desired operation. Right? So, I need to be able to calculate what is the phase of a beam after it has traveled some distance. Alternately, I could look at and say, I know all the properties of the beam here. If the beam were traveling through free space or through a medium, homogeneous medium, I can use this expression and say, this is what the beam would look like at this plane. Now, if it doesn't look like that, I know what aberration has been caused by this propagation. And I can correct for that aberration because I should have got a beam with this, I didn't. And so I can add a negative of the effects that made the beam deviate from what it should. I can correct for that. And some form of this is used when people are studying stars and the light that's traveling from a distant star comes through our atmosphere. Now, the distant star is a perfect point source as far as we are concerned. It's so far away, we can consider it a point source. I should get a nice perfect focus, assuming my optics of my telescope is perfect. But it doesn't happen because the beam gets distorted through the atmosphere. But since I know I should get a spot, I can correct for the distortion. And in fact, there's a measure of the distortion that it's seeing. Right? So there's so many things. You could use this to say, I expect a beam to look like this. It doesn't. So this is a measure of the distortion. This tells me something about the medium that it traveled through. Maybe I use this as a sensor. So there are many, many reasons why you want to be able to calculate. Just maybe that you want to be able to study propagation, or for all these other reasons. But you always need to have an expression for the beam, and that expression is going to tell you exactly what happens to the beam as it propagates. Okay. So for the Gaussian beam, if we look at the spatial variation, what I get is this expression. Okay. Now, just to give you some background, so that it's not really that I pulled this equation out of a hat. The equation that was solved, the original equation that was solved to arrive at this, is actually the wave equation. The wave equation takes, of course, into account both the spatial and time variation of a wave. So it's the del squared operator. Let's say my wave is psi minus 1 over v squared del dou squared psi by dou t squared is 0. Right? This is the original wave equation that we are solving. But this equation, of course, is a function of space and time. And in a lot of cases, we can neglect the time part when you're just studying the wave. Finally, of course, if you want the full description of the wave, you need to include the time part. But if you are looking only at the spatial variation, this equation will reduce to what's called the Helmholtz equation, which is only an expression of, and I put it in terms of electric field right now. Okay, so this is just it's a function of space. So I've kind of gone a step before this solution. Okay, I'm again trying to justify why the solution is acceptable. Now, if I didn't know anything, if I didn't make any of those assumptions, one point that I could consider was the solution to this, one possible solution is to say I have an amplitude and I have a phase. Okay. So here I have not made any assumptions. Now, if I substitute this, so let's call this equation 1 and this equation 2. If I substitute equation 2 in equation 1, I'm going to get, so this is E, I'm going to get dou squared E naught by dou x squared, dou squared E naught by dou y squared. Of course, there's a e power j k z there. There's this k squared E there, which is, I'm not writing out x, y, z of E naught, but everywhere please note E naught is a function of x, y, z. Okay. And I'm going to have dou squared by dou z squared of E naught e power j k z. Right? This is equal to 0. So I can just concentrate on this part for the moment, and that is going to be nothing but dou by dou z of the first derivative of these. So I'll have dou E naught by dou z e power j k z plus E naught j k e power j k z. And if I take this derivative again, I'll have dou squared E naught by dou z squared right? So if I now write this part along with this equation, what will happen is I have a jk squared here, so I have a negative term. So finally, and everywhere, every term has e power jkz, so that's going to cancel throughout. And finally, what you'll be left with is dou squared E naught by dou x squared plus dou squared E naught by dou y squared plus 2jk dou E naught by dou z, and you will have one more term, and that is the term dou squared E naught by dou z squared equal to 0. And again, I could go back to my variations for this wave and say, well, we are saying dou E naught by dou Z is a slow variation. So again, I'm taking into account the fact that the variables x and y are much less than z. So the variation of the amplitude with respect to z is a slower variation than the variation of the amplitude with respect to the lateral. What does that mean? It means as the beam propagates, the changes in the amplitude in the lateral extent are far more dramatic than the changes in the amplitude as it propagates along the z-axis. Yes, of course, there are changes as it propagates along the z-axis. Think of a wave that you're bringing to focus, right? At the plane that the wave leaves the lens to the plane where the focus has occurred, of course, the amplitude has changed, but the amplitude has changed greatly in the lateral region. Much more, that variation from exiting the lens to the focal plane slowly happens, right? So, this is a slow variation compared to dou squared by dou x squared and dou squared by dou y squared. And that's why we say this is an even slower variation and you can neglect it. So the equation that is actually solved to arrive at the Gaussian beam expression that I had written above, the equation that is actually solved is this equation. It's derived from the spatial Helmholtz equation, and you're taking into account the fact that you say this variation dou E naught by dou Z is a much slower variation than these. So I'm building all the groundwork for the Gaussian beam derivation, but we're not going to do the Gaussian beam derivation. Okay? But I didn't want to just give you that Gaussian beam expression because it's quite daunting to see all those terms and not have a sense or idea what those terms mean. So this expression, I didn't explain all the different terms there, right? So we recognize some of those terms now. We know what they are doing to the wave. But we didn't talk about what is omega of z, what is capital of R of z, what is zeta of z. Okay? So let's do that now. So R, capital R of z relates to the radius of curvature of the wave front. What do we mean? Again, if I think of a plane wave, I would draw it like this and I would say its wavefront can be considered to be planes. In fact, what are the rays? We've been talking about rays all this time. The rays are nothing but the normals to these wavefronts, right? So the rays are normals to the wavefront. So in a plane wave, we had these plane surfaces spread out to infinity, and they repeat every time the wave, we look at them every time the wave has traveled 2 pi, a phase of 2 pi. Okay. What are the wave fronts of a spherical wave? What's a wave front of a spherical wave? It's the spheres. The spheres around the origin are the wave fronts of a spherical wave. What are the wave fronts of a Gaussian beam? So the Gaussian beam is a really interesting beam. In some places, it has a very plane wave-like nature. In some other places, when I say places, what do I mean? As it propagates, at some places, during its propagation, it's going to appear like a plane wave. In other places, it's very similar to a spherical. It's similar to these waves, right? How do I draw the wave fronts of a spherical, of a Gaussian beam? Well, they are it depends greatly on where I am drawing them. But if you look at any textbook, what they will draw for you, if they're showing you a Gaussian beam propagating, is they'll draw something like this. This is a side view. So this is a Z direction. So the overall, the general direction of the wave is one direction. That is its plane wave nature. And yet, if I were to look at the cross section, it's not that it spreads out to infinity. The cross section anywhere at any plane would be Gaussian in nature. That's why it's called a Gaussian beam. That means the amplitude of the wave or the intensity of the wave dies down as you go out. Now I'm drawing a cross section. This is a cross section. So this is in the Y direction. This is in the X direction. So as you go sidewards, the amplitude dies down, clearly showing this is a wave with finite energy. It doesn't spread out to infinity. And any cross section I take is going to have this Gaussian nature. Only when the wave has spread out a little more, this beam or the peak is happening at a lower place and the spread is more. But it's Gaussian anywhere. Okay? And to talk about the wavefront, I have to be specific about where along its propagation. So there is a place where you have the minimum beam waste. That waste is called omega naught. So this is 2 omega naught. Okay, and that's the omega naught that you're seeing here. This is the minimum beam size for this Gaussian beam. Omega of Z is the parameter that tells you what is the beam radius at any value Z. Because you can see a plane wave, I assume it has the same radius or the same diameter as it propagates. Right? But a Gaussian beam, you can see from the way I've drawn it, it comes down to a narrow point and then it's diverging again. Right? So it has a certain omega of Z. Omega is relating to the radius. Okay, so if your diameter would be 2 omega of Z. But if I go to another value of Z, it has a different value of omega. Right? And Z is measured from this beam waist. This is always considered the E origin. This is Z equal to 0. So this is the distance Z for which you have this omega of Z. And then this would be Z1 and you would have omega of Z1 here, and so on. I didn't say there's no variation, it's a slow variation. Okay. So we have not neglected, we didn't neglect dou E naught by dou Z. That is retained in the expression. We are saying that itself is slow compared to the variation with respect to X and Y. Right? That is slow, but we retained dou E naught by dou Z in our expression. We said it is slow and therefore the second derivative is even slower and that we neglect. Okay. Now, in all of these derivations, even when we did ray optics, you would have seen, you talked about third order aberrations, fifth order aberrations, or when we arrived at the expression for a lens, so in your derivation for the refraction at a curved surface, you had a cosine term and we neglected all the higher order and we said, let's assume that it is 1, right? I can always do the derivation, repeat the derivation, taking the next term into account as well. And that's how you arrive at your third order, fifth order, seventh order. So even here, this is a general expression for a Gaussian beam where we say the second derivative, dou squared E naught by dou Z squared, is very small compared to the variation with respect to X and Y. That it's varying. No one is saying it's not varying, but it's so small compared to the transverse variation, it's negligible. In certain applications where the dimensions are such that it's not acceptable to make these assumptions, you need to be so accurate, or the variations are not negligible, you would go back to the derivation and say, I will not neglect that term, I'll keep that term. Why do we neglect it? Because in most cases, we have neglected it. That means there's an error factor in our solution, but that the error introduces probably is smaller than the errors we're getting from other aberrations. You don't see that error. And in any application where it's going to be so sensitive, you would go back and say, let's include all the terms. Today's class was just an introduction to Gaussian beams, okay? As I said, if you are interested in the details of it, please do go refer to that paper that I mentioned, or there are textbooks which will have the derivation. But the idea for us again is, I want to shift your focus now from rays to waves, so that we can now start looking at, because not every system can be analyzed using rays. If the wave nature, it cannot be neglected, and in many cases it cannot be, then just even to design my optical systems, I must be able to take this into account, okay? And so we're just shifting our focus so that we're able to take the wave nature into account. We'll look at the Gaussian beam in more detail in tomorrow's class. Good morning. So we've moved on to the next topic, Gaussian beams, and that's what we spent yesterday's class on. We did not do a formal derivation of the equation, but we looked at how the Gaussian beam is different from a plane wave and a spherical wave, two beams that we are familiar with, and using some logic based on how we expect the beam to behave or what kind of beam we're looking for, we explained the expression for a Gaussian beam, which has been derived elsewhere. Okay. What we were doing at the end of the class was to look at the different parameters in this beam a little closer. Okay. So this equation, as written here, very clearly demarcates the part of the beam which is the amplitude, relates to the amplitude, and the part which relates to the phase. But within this, you can see there are different terms. So we looked yesterday at r of z, which we call the radius of curvature of the wavefront. And to explain this, I had said, imagine you were looking at a Gaussian beam propagating along the z direction. If you were to take the cross section at any plane, it would have a different radius of curvature, okay, which is quite different from the plane wave or the spherical wave. This plane wave, at any plane, it has a planar surface. So its wavefront is a planar surface. The spherical wave, at any plane, its wavefront is a sphere. So the radius of that sphere is going to be different, but you have a sphere. Right? Whereas with the Gaussian beam, and we will look at this in more detail, the nature of that wavefront is changing as the beam propagates. Now, there were some questions about why I drew the beam like this. So just to clarify, if the beam were coming out of a source, so let's say I had a laser, and the beam emerging from this laser is a Gaussian beam, what I would expect from this source is not as I've drawn here with a increased radius or diameter, and then it decreases and then it increases again, but from the source would have the minimum radius and it would be diverging from there. Okay. So in other words, what I'm drawing in this figure is basically from this point onwards. Okay. Now, why is that? It's because a Gaussian beam is generated, it's one of the default modes generated by most laser cavities. But as long as the light is within the laser cavity, it's guided by the walls of the cavity. So it's not diverging there. But the moment the light leaves the laser, it starts to diverge. So its minimum radius, its minimum size is going to be at the point it exits the laser, it leaves the cavity. Okay. So the picture that I drew yesterday, this is just a general picture of how a Gaussian beam propagates, and this is going to become clearer as we go along. Remember, if we're talking about the light coming out of a source, it's coming out of a laser, it's coming out at its minimum size, and then because there's nothing to guide it anymore, the divergence starts. The point of importance is, unlike a spherical wave, even though there is divergence, it's not diverging in every direction as a spherical wave. It's not like a plane wave which theoretically has zero divergence and continues along one direction with the same size everywhere. Okay, there is some divergence, but it lies somewhere between these two. And in fact, we are going to see, not only does it lie somewhere between these two, these values of the radius as well as the divergence depend on where along the path of travel you're looking at the beam. Okay, now I have been using the word radius, so you have to be very, very careful, because the R of Z that I've written down here, capital R of Z, this is the radius of curvature of the wavefront, which is different from the diameter of the beam. Okay, so I could say, so in fact the radius here, and let's say this was the optical axis, it's symmetric about the optical axis, then I would say this is omega of Z, where Z is this distance. Z is always measured from the minimum size, and the diameter therefore is 2 omega of Z. So the radius of the beam at Z, okay, so radius of the beam is omega of Z. Okay, we had the same idea when we were doing geometric optics, and we talked about the size of your lens, the diameter or the radius of your lens, opposed to the radius of curvature of the lens, right? So do not get confused with these two parameters, both very important but completely different. Okay, so R of Z actually has this expression, okay, we will come back to this. I right now just want to give you these expressions. Okay, we also have omega of Z, and now we already know this is the radius of the beam, but I can write it in terms of the minimum spot, okay. So what is omega naught? Omega naught is the minimum spot size. So I'd say minimum radius, but typically for a Gaussian beam we don't say minimum radius, we will say minimum spot or minimum spot size. So in the example where I gave of the light emerging from a laser, the minimum spot is this value here, or other words, the value, it's omega of Z at Z equal to 0. Okay. So what this expression for omega of Z is telling us, as the beam propagates, it has this minimum value. As the beam propagates, there's a change, and that change is dependent upon Z, how far you have traveled away from the minimum spot, and it is also dependent upon this parameter Z naught, which is given by this relationship. Okay. Now, if we had done a formal derivation, in the course of the derivation, these terms would have been developed. I am just giving you the expressions now. Okay. Z naught is often called the Rayleigh range of the Gaussian beam, or it's sometimes called the confocal parameter. And in today's class, these parameters or the significance of these parameters ought to become clearer. So one point should be becoming clearer to you. When we talked about the plane wave, in order to describe the plane wave, I used an amplitude and a direction. With the spherical wave, I would need an amplitude and the origin of that point source from which the wave originates. But with the Gaussian beam, I do need an amplitude, I do need a direction, but I also need this omega naught or z naught, because omega naught and z naught are related. Right? So I need the wavelength as well. Right? So the Gaussian beam, in order to describe it fully or to understand it fully, there are few more parameters involved. Yeah? And that is typically why when you're introduced to the concept of beams that are solutions to the wave equation, you're normally introduced to the mathematically simple ones, although they are practically impossible to generate. Right? But there's very simple, the expression that describes them is simple, and with that simple expression, you get the idea that as the wave propagates, its phase is changing. From the expression, you can get information about the phase, the direction, and so on. Okay? Those same concepts are being applied here, but the way the Gaussian beam, or rather the change in the Gaussian beam as it propagates, or the effect of propagation on a Gaussian beam, is very, very different from that of the plane wave and the spherical wave. Okay. Okay, so I think we have covered all the parameters in this expression. Remember, rho was the parameter just taking the transverse coordinates into account. Okay, and of course we'll come back to zeta as well. Okay.